transition to high-voltage electric vehicle architectures has exposed a critical material bottleneck. At motor speeds exceeding 20,000 RPM, conventional steel bearings suffer from electrical discharge machining. Stray currents arc through the lubricant, causing micro-welding and rapid mechanical failure. Automotive manufacturers have standardized on hybrid ceramic bearings utilizing silicon nitride. However, the raw material supply chain is highly concentrated. Two Japanese producers, Ube Industries and Denka, control 84.8% of global high-purity powder capacity. Ube Industries utilizes the silicon amide pyrolysis method to achieve the necessary purity. Global demand has expanded at a 22.4% compound annual growth rate since 2020. This rapid growth has reduced the global spare capacity margin to less than 11%. The scarcity of high-purity powder has directly impacted downstream automotive manufacturing. Lead times for precision, hybrid ceramic bearings escalated from 12 weeks in 2020 to 52 weeks in 2024. This surge directly tracks the market penetration of 800-volt drivetrains. During this same period, the price index for high-purity silicon nitride powder rose by 210%. High energy intensity in precursor synthesis and slow capacity expansions have capped output. Automotive manufacturers cannot easily substitute these components. High RPM drivetrains operating above 20,000 RPM require the dielectric properties of ceramic bearings to prevent catastrophic failures. The transition to high-efficiency silicon carbide inverters remains physically bound by these chemical processing limits. Alternative synthesis routes, like direct nitridation, struggle to meet strict automotive standards. Direct nitridation of silicon powder fails to consistently achieve the 95.0% alpha phase purity required for high-fatigue applications. This structural deficiency leads to premature mechanical failure under high rotational stress. Furthermore, excess oxygen content in alternative powders degrades grain boundaries. This degradation causes the ceramic balls to fail at high speeds. Iron impurities must also remain below 20 parts per million to prevent electrical conductivity paths. These strict chemical parameters protect the dielectric integrity of the bearing. Consequently, the automotive industry remains dependent on the specialized amide pyrolysis process. This material reality limits the speed of the global electric vehicle transition. The rapid scaling of offshore wind turbine architectures has outpaced the civil engineering capacity of maritime ports. To lower the levelized cost of energy, manufacturers have expanded turbine capacities from 5.0 megawatts in 2015 to 15 and 20 megawatt platforms today. This transition has driven a nonlinear increase in component mass and physical dimensions. Modern nacelles now exceed 820 metric tons, requiring specialized quayside load-bearing capacities. Legacy port infrastructure at Esbjerg remained capped at 40 metric tons per square meter. This structural deficit prevents the handling of 15 megawatt-plus turbine components without risking quayside structural failure. By 2030, planned 20-megawatt turbines will feature nacelles weighing 1,100 metric tons. These systems will require 70 metric tons per square meter of bearing capacity. This requirement exceeds even the current expansion designs, threatening to cap future turbine scaling. The lag in civil engineering projects directly delays regional decarbonization targets. The cumulative North Sea offshore wind installation backlog is projected to peak at 4.2 gigawatts in 2025. This bottleneck directly correlates with the delayed expansion of the Esbjerg terminal. Soil consolidation and marine dredging requirements prevent the new 500,000 square meter quayside area from reaching operational status until late 2027. This multi-year timeline leaves developers without adequate pre-assembly and storage space. The physical limits of landside integration have become the primary constraint on offshore deployment. This terrestrial bottleneck is compounded by a shortage of specialized maritime assets. The global fleet of wind turbine installation vessels capable of handling 15 megawatt-plus systems remains highly constrained. The fleet is projected to grow from just 2 vessels in 2022 to 11 by 2027, leaving little margin for operational delays. The transition to 5G telecommunications and high-voltage electric vehicles has placed unprecedented stress on passive component supply chains. A single premium electric vehicle requires up to 10,000 multi-layer ceramic capacitors. These components rely on ultrafine barium, Titanate dielectric powder to stabilize voltage and prevent electrical noise. The production of this critical material is highly concentrated. Two Japanese chemical companies, Sakai Chemical Industry and Toda Kogyo, control 75% of the global merchant market. This creates an acute geographic and industrial bottleneck for advanced electronics. High-performance capacitors require hydrothermal synthesis to prevent particle agglomeration. This liquid phase process requires specialized autoclave reactors operating at high temperatures and pressures. Alternative synthesis methods cannot consistently produce the sub-100 nanometer particle sizes required for modern high-density applications. To increase capacitance within standardized footprints, manufacturers must stack hundreds of ultra-thin dielectric layers. Since 2015, dielectric layer thickness has decreased by 79%, now reaching 0.25 microns. This shrinkage forces a corresponding reduction in barium titanate particle size to under 35 nanometers. At these microscopic scales, material uniformity is critical. Any particle size variation exceeding 10% of the layer thickness causes localized dielectric breakdown. In high-end automotive capacitors with over 1,200 layers, such defects can reduce production yields by up to 40%. Furthermore, the industry is approaching an absolute physical limit at 20 nanometers. Below this threshold, barium titanate transitions from a ferroelectric to a paraelectric state. This phase change collapses the dielectric constant from approximately 3,000 to under 200, rendering the material useless for high-capacitance applications. The Iberian Peninsula operates as a structural energy island within the European Union. Despite possessing over 30% of Europe's total regasification capacity, Spain and Portugal remain physically isolated from the broader European gas grid. This isolation is enforced by the Pyrenean mountain range. The landside pipeline network crossing the Franco-Spanish border is limited to just 2 interconnectors. Together, the Lerau and Biriadu pipelines cap maximum export capacity to France at just 8.0 billion cubic meters per year. This represents a permanent ceiling on Iberian energy integration. During the peak of the European energy crisis in 2022, Iberian LNG imports rose to 36.5 billion cubic meters. Yet, 35.5 billion cubic meters of regasification capacity sat idle. The Pyrenean bottleneck allowed only 11.1% of Iberia's total capacity to flow north. This physical bottleneck has driven severe economic inefficiencies across the European continent. To replace Russian pipeline gas, Central European nations bypassed low-cost Iberian infrastructure. Instead, they deployed temporary floating storage and regasification units in the North and Baltic Seas. These emergency marine deployments came at a massive premium. German floating terminals cost an estimated 220 million euros annually for 15.0 billion cubic meters of capacity. In contrast, the permanent deepwater terminal at Sines operates at just 45 million euros per year. The structural solution was the proposed mid-cap pipeline across the Pyrenees. This project would have added 7.5 billion cubic meters of annual capacity for a one-time capital expenditure of 450 million euros. Regulatory vetoes and environmental disputes canceled the project, locking in high-cost maritime workarounds. The scaling of 3D NAND flash memory is fundamentally constrained by the physics of ultra-high aspect ratio plasma etching. To achieve higher bit densities, manufacturers must etch vertical channel holes through alternating stacks of silicon oxide and silicon nitride. In state-of-the-art architectures, these holes must penetrate depths exceeding 5 to 8 micrometers. This physical scaling has driven a massive surge in demand for semiconductor-grade carbonyl sulfide. Global demand has expanded at a compound annual growth rate of 22.9% since 2018. Meanwhile, effective purification capacity has lagged, growing at only 12.7%. A structural deficit emerged in 2021 at approximately 30 metric tons. This deficit is projected to expand to 300 metric tons by 2026. Advanced memory fabrication facilities are now operating with historically low inventory buffers. As memory layers stack higher, the process window for successful etching shrinks. Carbonyl sulfide flow rates in the plasma chamber must scale nonlinearly to maintain sidewall passivation. Flow rates rise from 5 standard cubic centimeters per minute at 64 layers to 150 at 320 layers. The protective sulfur polymer layer must also thicken to withstand prolonged high-energy ion bombardment. Without this precise passivation, lateral etching causes channel bowing and structural collapse. Consequently, minor variations in chemical purity cause etch defect rates to spike. At aspect ratios exceeding 100:1, defect rates rise from 0.12% to 5.40%. This exponential risk profile makes advanced memory fabs highly sensitive to chemical consistency. The physical limits of silicon are now governed by sub-parts per million chemical purity. The supply chain supporting this critical process is highly consolidated. Two Japanese chemical manufacturers, Resonac and Kanto Denka Kogyo, control over 60% of the global merchant market. This geographic concentration exposes the entire semiconductor industry to single point-of-failure risks. Expanding capacity outside of East Asia is constrained by severe environmental and regulatory barriers. Synthesizing carbonyl sulfide generates highly toxic and corrosive intermediates like carbon monoxide and hydrogen sulfide. Obtaining environmental permits for new synthesis facilities in Western jurisdictions is extremely difficult. Furthermore, qualifying a new purification source at a Tier 1 memory fab requires 24 to 36 months. Fabs must verify that metal contamination remains strictly below subparts per billion limits. This lengthy qualification timeline prevents rapid substitution during supply disruptions, locking in the current geographic monopoly. The port of Gdynia has transitioned from a commercial Baltic gateway into a critical dual-use military and agricultural node. Following the blockade of Black Sea trade routes, Gdynia became the primary conduit for redirected Ukrainian grain and NATO heavy armor. This rapid maritime expansion has exposed a severe structural mismatch between wet-side handling and dry-side rail evacuation. While total maritime throughput at Gdynia expanded by 25.4% between 2019 and 2024, landside rail capacity contracted. Rail evacuation capacity dropped to 10.2 million metric tons due to infrastructure degradation on Polish railway line 201. This divergence has caused terminal dwell times to surge. Average rail transit delays for bulk cargo and military equipment escalated from 2.1 days to 14.2 days over the same 5-year period. The physical limit of the port is no longer determined by its berths or cranes. The bottleneck has shifted entirely to the terrestrial rail network. Primary landside bottleneck is Polish railway line 201. This corridor connects Gdynia to the southern industrial hinterland, but fails to meet basic NATO military mobility standards. The line's axle load limit is capped at 22.5 metric tons. This weight restriction prevents the transport of fully loaded M1A2 Abrams tanks on standard flat cars. Moving these 64 metric ton combat vehicles requires specialized, scarce heavy-duty rolling stock. Furthermore, only 15% of the corridor is electrified, and only 35% is double-tracked. These physical constraints limit maximum train lengths to 600 meters, well below the NATO standard of 740 meters. Heavy freight speeds average just 50 kilometers per hour. This structural deficit directly compromises the rapid reinforcement capability of NATO eastern flank during a regional crisis. Deepwater oil and gas wells exceeding depths of 5,000 meters operate at the physical limits of hydrostatic control. Traditional drilling fluids rely on suspended solid weighting agents like barite to achieve high densities. However, these solids precipitate under extreme thermal conditions, causing irreversible reservoir damage and plugging pore throats. To bypass these physical limitations, the offshore industry transitioned to clear, solids-free brines. While conventional halide brines, like zinc bromide, achieve high densities, they are highly corrosive to chrome alloy casings. They also pose severe environmental hazards in maritime environments. High-purity cesium and rubidium formate brines have emerged as the only viable alternative. They offer densities up to 2.30 grams per cubic centimeter without solid additives. Furthermore, they remain non-corrosive and thermally stable up to 220 degrees Celsius. Critical vulnerability of this technology lies in its extreme supply chain concentration. Following the 2019 acquisition of the Tanko mine in Canada by China's Sinomine Resource Group, the global supply of these high-density brines became monopolized. Sinomine now controls 86% of the global merchant market. This consolidation has driven a rapid escalation in operational costs. Average rental rates for high-purity formate brines rose from $1,200 per barrel in 2018 to $3,200 per barrel in 2024. This represents a 166% increase in raw material costs. To mitigate supply constraints, operators must adhere to a strict rental and reclamation model. Contracts now mandate a downhole fluid recovery rate of 98.0%. Consequently, any downhole fluid loss during drilling directly threatens the financial viability of multi-million-dollar offshore campaigns. The geopolitical rupture of 2022 abruptly severed Finland's primary inland maritime corridor. The Saimaa Canal passes through the Russian-leased Vyborg district. Following the imposition of sanctions, commercial transit through this 43-kilometer waterway effectively ceased. This sudden closure stranded the industrial logistics network of southeastern Finland. Prior to 2022, the canal carried over 1.3 million metric tons of raw timber and mineral aggregates annually. By 2023, this volume collapsed to near zero levels. The regional economy was forced to immediately reroute this bulk cargo overland. By 2024, rail and road networks absorbed 1.39 million metric tons of displaced freight. This represents a complete and permanent structural shift in Nordic industrial logistics. Rerouting bulk commodities from low-cost maritime routes to overland networks has imposed a severe economic penalty. Average freight costs for Finnish industrial operators escalated from 15.20 euros per metric ton in 2021 to 24.80 euros in 2024. This represents a structural increase of 63.1%. The domestic rail network was unprepared for this sudden influx of heavy cargo. Average transit and rail car allocation delays surged from under 2 days to a peak of 8.2 days. This logistical friction has created persistent equipment shortages at key industrial hubs. Simultaneously, the diversion of over 500,000 annual tons to road transport has accelerated infrastructure wear. Heavy timber and mineral trucks are degrading regional highways like Highway 6. This shift has transferred private logistics costs directly onto public maintenance budgets.